In this course, we're going to build a strong, practical foundation for modern Java programming by exploring something many developers learn only halfway: the powerful connection between core data structures and the fundamental methods every Java object inherits. Most tutorials teach lists, sets, and maps on one side, and methods like equals, hashCode, and toString on the other, but rarely explain how these two worlds depend on each other. Yet in real-world Java development, understanding this relationship is what makes your code efficient, predictable, and bug-free. We'll start by looking at the essential collections: lists, sets, maps, queues, and dequeues, and discuss when and why to choose each one. Then we'll deepen that knowledge by examining key object methods and contracts that determine how your objects behave when stored, compared, or sorted. Along the way, we'll explore best practices, common pitfalls, and modern techniques like collection factory methods, safer iteration patterns, and the superpowers hidden inside the map API. By the end of this course, you'll not only know what Java collections can do, you'll understand how to use them with confidence in any project. Lists are the most common and flexible data structure in Java because they preserve the order of elements and allow duplicates, making them ideal for sequences of items where position matters. They provide fast access by index, which is perfect when you need to retrieve or update elements at specific positions. The two main implementations, ArrayList and LinkedList, offer different performance characteristics. ArrayList is generally faster for reading and iterating, while LinkedList is better for frequent insertions or deletions in the middle, though it's rarely needed in modern code. Overall, when you need an ordered, flexible, and easy-to-use collection, a list is usually your first and safest choice. In this example, we create an array list and start adding elements to it, including duplicates, which lists fully support. We then retrieve the first element using getZero, showing how lists give fast, direct indexed access. The call to contains B demonstrates how lists rely on the equals method of their elements to check for membership, an important connection between objects and data structures. We also use collection sort items to show how lists can be easily sorted when their elements are comparable. Finally, printing the list displays its ordered nature, the sequence we inserted, with duplicates preserved. Overall, this small snippet highlights the essential characteristics of lists: ordered, indexable, duplicate-friendly, and tightly integrated with core object behaviors. The next data structure are sets. Sets are the perfect choice when you care about uniqueness rather than order or duplicates. Unlike lists, a set automatically rejects duplicate elements, relying on the element's equals and hashCode methods to decide whether something is already present, making these object contracts especially important here. Because sets don't store elements in a specific order, they're often faster for membership checks, making them ideal for tasks like filtering, deduplicating data, or representing collections where each element should appear only once. The most commonly used implementation is hashSet, which gives very fast insert and lookup performance, while linked hashSet preserves insertion order, and treeSet keeps elements sorted. Whenever your goal is to enforce uniqueness or quickly check whether something exists, a set should be your natural go-to structure in Java. In this snippet, we start by creating a hashSet, the most common implementation of the set interface. We add 3 elements, including a duplicate A, and the set automatically ignores the second insertion, highlighting its core guarantee of uniqueness. The call to contains B shows one of the main strengths of sets: fast membership checks, which rely on the equals and hashCode methods of the elements. We then remove A and print the set, and the result illustrates another important characteristic. Sets do not preserve any specific order, so the printed output may vary across runs. In just a few lines, this example captures what makes sets useful. They ensure uniqueness, they offer efficient lookups, and they depend heavily on correct object equality behavior. Maps are one of the most powerful and widely used data structures in Java because they let you associate a key with a value, giving you extremely fast lookups, updates, and replacements. Unlike lists or sets, which store individual elements, a map manages pairs, allowing you to model real-world relationships, like IDs and users, words and counts, or settings and configurations. The key property of a map is that keys must be unique, and Java relies on the keys equals and hashCode implementations to determine how entries are stored and retrieved. HashMap is the default choice for most use cases, offering excellent performance, while other variants like linked hashmap preserve insertion order and treemap keep keys sorted. Whenever you need quick access to data based on a unique identifier, a map is almost always the right tool, making it a central part of effective Java programming. In this example, we use a hashmap, which is the most common and efficient map implementation in Java. We insert a few key-value pairs, and when we call put A3 a second time, the map replaces the previous value for A, demonstrating that maps enforce uniqueness of keys, not values. The getOrDefault C0 call shows how maps let us safely retrieve values without risking a null, which is essential in real-world code. We then check for the presence of a key using contains key A, remove B, and finally print the map. The order of entries isn't guaranteed, which is typical for hashmap. This small example highlights the core ideas behind maps: fast lookups by key, automatic replacement on duplicate keys, and strong reliance on equals and hashCode to manage how keys are stored and retrieved. Queues and dequeues are specialized data structures designed for situations where the order of processing matters. A queue follows the classic FIFO principle, first in, first out, making it ideal for tasks like job scheduling, buffering, or any pipeline where elements must be processed in arrival order. A dequeue, on the other hand, is a double-ended queue that allows inserting and removing elements from both the front and the back, making it more flexible and suitable for algorithms like breadth-first search, undo-redo stacks, or any structure where both ends must be accessible. Implementations like ArrayDeque offer excellent performance without the overhead of linked list, and they avoid the capacity issues of old stack. Overall, queues and dequeues help you structure data flows cleanly and efficiently whenever you care not just about what you store, but also when and how it gets processed. In this example, we're using an ArrayDeque and demonstrating why it's such a flexible structure in Java. We start by adding elements with offerLast, which behaves like a normal queue-enqueue, and offerFirst, showing that we can also insert at the opposite end when needed. Using peekFirst and peekLast, we inspect the current head and tail without removing anything, which is ideal when you want to check what's coming next. Then, pollFirst and pollLast remove elements safely from either end, returning null instead of throwing an exception if the decay is empty. Finally, printing the decay reveals the remaining elements in their current order. Even in this small snippet, you can clearly see the two strengths of a decay: predictable FIOQ behavior when using the front, and extra flexibility when accessing both ends for more advanced logic. Before we go further, it's important to look at some core object methods like equals, hashCode, and toString, because they directly influence how your objects behave inside the collections we've just explored. These methods determine how elements are compared, how they're stored in structures like sets and maps, and even how they're sorted or displayed. In other words, understanding object methods isn't optional. It's what makes your collections work correctly and predictably. So in the next section, we'll dive into these fundamental methods and see how they shape the behavior of your objects throughout the Java ecosystem. The equals method defines what it means for two objects to be logically equal, and understanding when to override it is essential for writing correct Java classes, especially those used in collections. If you don't override equals, every instance is considered equal only to itself, which is fine when objects are inherently unique, like threads, or when your class simply doesn't need to support a meaningful equality test. It's also acceptable to rely on a superclass implementation when its behavior is correct, or when the class is private and you're sure no one will ever compare instances. But when you do override equals, it must obey the standard contract. It has to be reflexive, symmetric, transitive, consistent, and return false when compared to null. A proper implementation follows a clear pattern. Check if the argument is the same reference, verify the type with instance of, cast it, and then compare each significant field, using equals for most primitives, the appropriate compare methods for floats and doubles, and objects.equals for object references. By comparing the fields most likely to differ first, you keep the method efficient. The phone number example demonstrates this pattern and illustrates what a well-implemented equals looks like in practice. In this example, book is a small value object where we define logical equality by a single stable identifier, the ISBN. The method starts with the fast path. If the argument is the same reference, return true. Then uses instance_of to reject incompatible types. After casting, we compare only the significant field for equality, ISBN, using objects.equals to handle potential nulls safely. Notice that title and price are not part of equality here. That's an explicit business decision. Two book objects with the same ISBN are considered the same book, even if the title changes. Whenever you override equals, you must also override hashCode, because collections like hashSet and hashMap depend on it to group objects into buckets. The method must always return the same value for the same object during its lifetime. And if two objects are equal according to equals, they must return the same hashCode. Unequal objects don't have to produce different hashcodes, but doing so improves performance by reducing collisions. It's also important not to document or promise specific hashcode values, giving you the freedom to change the implementation later. A good hashcode combines the significant fields of the class in a stable way and distributes values well. In this snippet, we're generating a hashcode by combining all the significant fields of the book class. We start with the hash of ISBN, then multiply by 31, a common and effective multiplier, and add the hash of each additional field. For the double field price, we convert it to its bit representation so that two numerically equal prices produce the same hash. This pattern produces a stable, well-distributed hashcode that satisfies the key requirement. If two book instances are equal according to equals, they will definitely return the same hash value. At the same time, unequal instances are likely to produce different values, which helps secs and maps perform efficiently. This example also avoids exposing any specific hash formula to clients, keeping you free to change the implementation later. The toString method gives a human-readable description of an object, and because the default version inherited from object only prints the class name and a hexadecimal hashcode, it's almost never useful in practice. That's why it's recommended to override toString and return a meaningful summary of the object's important fields, something that helps during debugging, logging, or when printing collections. When you design this representation, you should be clear about whether the format is guaranteed or not. If you document the exact structure of the string, then you must keep it stable across future releases, because changing it would break clients that parse or rely on it. And whether the format is fixed or flexible, it's important that all the information exposed in toString is also available through proper accessor methods, so developers never have to extract data from the string itself. In short, a good toString makes objects easier to understand without becoming a source of hidden dependencies. In this example, toString returns a clear, human-readable summary of the most important fields, perfect for debugging and logs. Notice the key design choice. We don't promise a specific format in toString. The comment states it's not stable, which gives us the freedom to change it later without breaking clients. If a stable, machine-readable line is required, we add a dedicated method like toLogLine and document its format explicitly. This keeps toString helpful for humans and avoids hidden dependencies in production code. The comparable interface defines the natural ordering of a class, allowing objects to be compared to each other and automatically sorted by the Java standard library. When a class implements comparable, it provides a single compare_to method that tells Java whether one instance should come before, after, or be considered equal to another. This is what makes features like collections.sort, sorted sets such as treeset, and sorted maps like treemap work. A good natural ordering should be intuitive, stable, and consistent with equals, meaning that if two objects are considered equal, their compare_to should return 0. Typical examples include numbers sorted by numeric value, strings sorted alphabetically, or domain objects sorted by a single meaningful key, such as a username or ID. Implementing comparable gives your class a built-in, automatic way to participate in ordering-based operations throughout the Java ecosystem. In this example, the user class defines its natural ordering by implementing comparable_user. The compare_to method starts by comparing usernames alphabetically, establishing the primary sort key. If two users share the same username, we fall back to a secondary rule based on reputation, placing users with higher reputation first. This shows how natural ordering can combine multiple fields while still keeping the comparison deterministic and easy to understand. Because we use string compare_to for the username and integer compare for the numeric field, the logic stays clear and avoids subtle bugs. With this implementation, user objects can be sorted directly with collections.sort, used in sorted sets, or serve as keys in sorted maps, all without requiring an external comparator. While comparable gives a class a single built-in natural ordering, the comparator interface lets you define multiple different orderings for the same type without modifying the class itself. A comparator is simply an object that knows how to compare two instances, which makes it perfect when you need sorting rules that change depending on context, like sorting users by name in one place, by reputation in another, or by sign-up dates somewhere else. Comparators are especially useful when the class is not under your control or when it wouldn't make sense to bake one official ordering into the model. Modern Java makes this very convenient with factory methods like comparator.comparing, then comparing, and reversed variants, all of which allow you to combine fields and create expressive, readable sorting logic. Using comparators ensures your code stays flexible, avoids hard-coding a single ordering into the class, and keeps sorting behavior close to the place where it's actually needed. In this snippet, we show how Comparator lets you define multiple sorting strategies for the same class without changing the class itself. We start by creating a comparator that sorts users alphabetically by username. Then, we define another comparator that orders them by reputation in descending order, something that wouldn't make sense as a natural ordering, but is perfect for leaderboards or ranking views. Finally, the third comparator demonstrates how to combine rules. We sort by sign-up date first, and only if two users joined on the same day do we fall back to sorting by username. The use of comparator.comparing, comparing int, reversed, and then comparing keeps the code expressive and easy to read. This approach highlights the power of comparators. You can create exactly the ordering you need, exactly where you need it, without hard-coding anything into the model class. Auto-closable is the interface that allows objects to be used safely with Java's Try with Resources feature. Any class that implements auto-closable promises that it can release its underlying resources, like files, sockets, streams, or database connections, by providing a close method. This is important because many system resources must be explicitly released, and forgetting to close them can lead to memory leaks, file locks, or connection exhaustion. With Try with Resources, Java guarantees that the close method is called automatically, even if an exception occurs. This makes resource handling code safer, cleaner, and much harder to misuse. Classes in the standard library, such as buffered reader, input stream, output stream, and JDBC connection, all implement auto-closable. And implementing it in your own classes is straightforward whenever you manage something that needs explicit cleanup. In modern Java, using auto-closable correctly is the standard way to write robust, exception-safe, resource management code. In this example, the temp_file class manages a temporary file and implements auto-closable so it can be used safely inside a try-with-resources block. The constructor creates the file, and the close method handles the cleanup by deleting it. When we use temp_file inside a try-with-resources statement, Java automatically calls close at the end of the block, even if an exception is thrown. This pattern is ideal whenever your class owns something that needs explicit cleanup, like files, streams, sockets, or database handles. By implementing auto-closable, you ensure that resource management stays simple, predictable, and exception-safe, reducing the risk of leaks or forgotten cleanup logic. Before working with collections effectively, it's crucial to understand the object contracts that Java relies on behind the scenes. These contracts define how objects behave when compared, sorted, or stored, and collections assume that your classes follow them correctly. The most important one is the equals hashCode contract, which states that if two objects are equal according to equals, they must always return the same hashcode. Breaking it leads to unpredictable behavior in hashmap and hashset. There's also the Comparator contract, which applies when your class implements comparable. If Comparator says two objects are equal, that result should be consistent with equals, and the ordering must be transitive and stable. Finally, object contracts highlight the dangers of mutability inside collections. If an object used as a key or element is modified after being inserted, especially if fields involved in equality or ordering change, the collection may no longer be able to find it or maintain its order correctly. These contracts aren't just formal rules. They are essential guarantees that keep Java's collections correct, efficient, and predictable. Now that we've covered the object contracts that make collections behave correctly, let's move from theory back into practice. In the next part of the video, we'll look at a set of simple but incredibly useful techniques that make working with lists, sets, and maps much more efficient. These include factory methods that remove boilerplate, safer ways to construct and modify collections, and common operations like sorting, reversing, and shuffling that you'll use all the time. These techniques will help you write cleaner, more expressive Java code, and they'll also reinforce how the object behaviors we just discussed influence everyday collection usage. Factory methods like list.of, set.of, and map.of give you a modern, concise way to create small, fixed collections without the usual boilerplate. They produce immutable collections, which means they can't be modified after creation, a feature that helps make your code safer, especially when passing data between methods. These methods also fail fast when given nulls or duplicates, preventing subtle bugs that can occur with mutable constructors. Compared to the old pattern of creating a new collection and repeatedly calling add, factory methods are shorter, clearer, and express your intent directly. Here are the elements. They also fit naturally with functional and declarative styles introduced in modern Java. Using them will make your examples more compact, your APIs easier to use, and your data flows more predictable. One of the biggest advantages of using lists in Java is that you can easily change their order to match your needs. Sorting lets you arrange elements based on their natural ordering, or using a custom comparator, giving you full control over how data is presented. Reversing is useful when you want to flip an existing order without redefining it. And shuffling is perfect for randomizing elements in scenarios like simulations, games, or test data. Modern Java makes all of this straightforward through utility methods in collections and the list interface. And understanding when to use each operation helps you manipulate sequences clearly and predictably. In this snippet, we start with a simple list of names. Calling names.sort with the natural order arranges them alphabetically. Then we use collections.reverse to flip the list, which is great when you want the opposite order without resorting. Finally, collections.shuffle randomizes the elements, giving you an easy way to introduce randomness for demos or testing. Each operation is straightforward and shows how Java gives you simple, expressive tools for reshaping a list's order with minimal code. When iterating over collections, Java gives you several ways to loop through elements, but not all of them support modifications safely. The enhanced for loop is great for readability, but it cannot handle structural changes during iteration and will throw a concurrent modification exception if you remove elements directly from the list. Safe iteration requires using an explicit iterator and calling its remove method, which is the only supported way to remove items while iterating. Understanding the difference between these patterns is essential, because modifying a collection incorrectly can lead to subtle bugs or crashes at runtime. By recognizing when you need to mutate a collection and choosing the right iteration pattern, you keep your code both correct and predictable. This example shows why understanding safe iteration matters. In the first loop, we use the enhanced for loop and try to remove an element directly from the list. Even though this looks natural, it immediately triggers a concurrent modification exception, because the for each loop uses an internal iterator that isn't expecting the collection to change. In the second part, we explicitly create an iterator and call remove on that iterator, which is the only supported way to delete elements while iterating. This pattern ensures that the iterator and the collection stay in sync, avoiding runtime errors and keeping the logic predictable. It's a small but important distinction that helps you write more robust code when working with mutable collections. Maps in Java offer far more than basic get and put. Modern methods like getOrDefault, computeIfAbsent, and merge allow you to handle missing keys, build group structures, and accumulate values without verbose checking logic. These operations make map usage safer and more expressive by eliminating common patterns such as checking for null or manually creating inner collections. They also help avoid subtle bugs caused by missing initial values or inconsistent updates. Understanding these superpowers lets you write shorter, clearer code that expresses your intent directly, while leveraging efficient built-in behavior instead of reinventing it. In this example, getOrDefault lets us safely retrieve a value while supplying a fallback when a key isn't present, which avoids null checks and simplifies lookup code. ComputeIfAbsent is especially powerful because it creates a new value only when needed, in this case, a list for a category, so we can immediately add elements without worrying about initialization. Finally, merge provides a clean way to accumulate counts. Instead of checking whether the key exists and manually updating the value, we simply tell the map how to combine the old and new values. These features make your map code far more concise and expressive, eliminating a lot of boilerplate and reducing the chance of errors. We've now walked through the core pieces that make Java's collections and object model work together smoothly. You've seen how lists, sets, maps, and queues each solve different problems, and how their behavior depends directly on the object methods you provide, especially equals, hashCode, toString, and comparisons. We looked at the contracts that guarantee predictable behavior, the dangers of mutating objects after storing them, and the modern techniques that make working with collections cleaner and safer, from factory methods to sorting, iteration patterns, and the advanced features of maps. With these tools, you now have a solid, practical foundation for writing Java code that is efficient, expressive, and reliable. In the next part of the course, we'll build on this base and explore how these ideas connect with higher-level features in modern Java, helping you write code that's not just correct, but elegant and scalable.